So we have just look back what we have learned in the previous lecture as the once again just to summarize and to look back, and then we just discussed in the previous lecture. I mean the what which light is important for photochemical reaction, how much amount of energy we are giving to the molecule, what happens, and so on and so forth. Now coming to the next one is the classification or type of photochemical reaction. The photochemical reactions have been classified into three different types on the based on the potential energy curve for the ground state and the excited state. The three different types are adiabatic, the adiabatic, non-adiabatic, and hot ground state. Adiabatic photochemical reaction. Second one is the non-adiabatic photochemical reaction, and third one is hot ground state. Hot ground state photochemical reaction. Now these are the three different types of photochemical reaction, which are three different types of photochemical reaction have been classified based on the excited state and the ground state potential energy curve. And these reactions are self-explanatory, and then it can be well understood by just looking into the energy two components. Let's say, for example, this is the reaction coordinate, and this is the energy, or in other words, causes the progress of the reaction. And then so they have a so this is the ground state. This is the ground state curve. The ground state curve. This the molecule A is in the ground state. Molecule in the ground state, and then the molecule, and then goes to, and then molecule, say for example, say this is the this is a reactant R, and on absorption of light goes to reactant R star H nu. This is the reactant in the ground state, and then reactant in the excited state. So reactant in the ground state, and this on absorption of light goes to an excited state. Now this reactant excited state proceeds all the way on the excited state curve. This is excited state ground state curve. This is excited state curve. The state curve proceeds in the excited state curve and goes to the product. So it goes transformed to the product in excited state. So this is how this way of representation of a photochemical reaction is an example of a adiabatic photochemical reaction, where molecule R, the R is a reactant. This is the reactant. Reactant in the ground state, on absorption of light, H nu, then goes to an excited state of the reactant. This is excited state reactant. R star. R star reactant in the excited state moves on the surface of the excited state curve and transforms all the way, goes to the product, excited state product. This is P star is the excited state of the product, and then this come back to ground state product by losing light. This is the this is mainly the fluorescence and phosphorescence. So this is if the reaction is proceeding via this, where these this way of representation, or the follow up of the transformation of reactant R, transformation of reactant R to product P. Transformation of reactant to the product in this manner, where we have a two representation. The ground state curve is the excited state curve. The reactant in the ground state, uh, react, reactant in the ground state on absorption of light goes to an excited state of the reactant. The reactant in excited state moves on the surface of the excited state and transforms to the product in a excited state. This is the product in excited state. And then a product in excited state loses light, either in the form of fluorescence or phosphorus, goes to the product in the ground state. So if the reaction is proceeding via this type of representation, you call it as a adiabatic adiabatic photochemical reaction. Now the next representation is the I mean, call it as a non-adiabatic or diabetic photochemical reaction. So we can represent this in the same way, and then slightly different. So I will just remove this. So as usual, we have this is the second example. We have a reaction coordinate, reaction coordinate. That is the progress of the reaction, progress of the reaction. There is the energy, and then we have two curves: ground state curve and an excited state curve. So it's slightly different. It's like this. This is the ground state curve. Ground state curve. This is the reactant transforming to product, and then the reactant on absorption of light, and then the excited state curves looks like this. And then you see the reactant is slightly, it's too high. So reactant on absorption of light, H nu, goes to a excited state of the reactant. There is a second, there is a presentation of second type of photochemical reaction called as a non-adiabatic photochemical reaction, where the reactant R on absorption of light goes to an excited state of the reactant. This is the excited state, ground state curve. This is the excited state curve. This is the reactant in the ground state, and then reactant in the excited state. And then the reactant proceeds on the surface of the excited state, and at one stage of the during the course of the reaction coordinate. At one stage, and during the course of the reaction, excited, this is the ground state curve. The excited state curve and ground state curve are coming to very close to each other. So there is a switching over of the excited state of the reactant to the ground state, and then there is a possibility of going back to ground state, and the rest of the reaction is taking place on the ground state curve and is going to the product P. So this is the reaction is proceeding via this way. Then you call it a non-adiabatic reaction, and where so it's a simple. We have two. One is the x-axis is a reaction coordinate, or we call it the progress of the reaction. This is the energy. The reactant. These are the two curves. This is the ground state curve. This is the excited state curve. And then reacting the ground state on absorption of light goes to excited state, and then the excited state reaction proceeds, and during the course of the reaction, both the curves, ground state curve as well as excited state curve, come very close to each other, and then there is a switching over. There is a switching over of the the excited state reactant to the ground state curve, and rest of the reaction takes place on the surface of the ground state. And then there is a two possibilities: the reactant can come back to excited state reactant can come back to ground state, or it can transform to the product. So this is we have a it is a very best example of a cis-trans isomerization of alkene. So, for example, R in cis form, and then R in the transform, and then here it is not possible the transform cis form trans to cis. So we know that the trans is more stable than cis, but it is possible to convert more stable to the less stable through photochemical method, but the reaction is reversible. And hence, since the reaction is reversible, it is not possible to undergo the reaction through 100% conversion, and that's why it is always in equilibrium. And that is the best example of it. And this goes via the non-adiabatic photochemical reaction, where the excited state curve and the ground state curve during the course of reaction they come very close to each other. The excited state reactant at one stage can switch over the ground state curve, and then when it is and the rest of the reaction takes place on the ground state curve, and then when it takes place on this one, there is a possibility of coming back to ground state, and then there is a possibility to transform to the product. So if the reaction is proceeding via this, then we call it as the we call it as a the non-adiabatic. The third one is the hot ground state curve. There is the involvement of an intermediate, and then this can be represented uh, in this way, where the reaction is taking place via defined intermediate. And then I mean the reaction is more or less same coordinate. We have a x-axis reaction coordinate, a progress of the reaction energy. The only the representation of this is like this, and then the here. So this is the reactant R on absorption of light goes to an excited state, and then there is a switching over to the ground state curve, and then this is a very small barrier, and then we cross over and goes to intermediate. So this is going via an intermediate, and then it can cross over to the small barrier of the intermediate and then transform to the product. So if the reaction is proceeding via an intermediate, then the reaction is called as a hot ground state. So these are the photochemical reactions have been classified into three different types, depending based on the potential energy curve of the ground state as well as excited state, where these three types of photochemical reactions are adiabatic photochemical reaction, second one is non-adiabatic photochemical reaction, and third one is hot ground state photochemical reaction. In the first one, the ground state potentially curve ground state and excited states are two separate pathways, and the reaction on the absorption of light goes to excited state, and then whole reaction takes place on the surface of the excited state, and reactant R converted to reactant R star is connected to product star in the product in the excited state, which comes back to ground state product via losing light, either fluorescence and phosphorescence. Second one is a non-adiabatic reaction, where the energy curve of the ground state and excited states are during the course of the reaction they are very close to each other, and then there is a switching over takes place, and then from the excited reactant to the ground state curve, and then the rest of the reaction takes place on the ground state curve. And then when it rest of the reaction takes place on ground state curve, then there is a possibility of the coming back to excited reactant to the product starting material, or excited reactant can transform to the product P, and hence this is an example of a reversible reaction, and best example is cis-trans isomerization of an alkene, where it is possible to convert more stable thermodynamically more stable trans alkene to cis alkene, but since the reaction is via non-ideal person, it is not possible to convert 100% because of the stability of the trans, and the reaction is in equilibrium, and then so it has to be the product has to be separated by different techniques. And third one is a hot ground state. Hot ground state photochemical reaction, where there is an involvement of a definite intermediate I, and then which R on absorption of light goes to excited state, and then switch over to the ground state, and then there is the involvement of an intermediate R which crosses over to a small barrier and transforms to the product. So these are the three different types of photochemical reaction. We call it a classification of photochemical reaction, or we call it as a the type of photochemical reaction: adiabatic, non-adiabatic, and hot ground state based on the potential energy curve movement. Now, as far as the quantum yield and efficiency of photochemical reaction is concerned, is very important to know what is whenever we do the chemical reaction, we always talk about what is the yield of the reaction, and hence efficiency of a photochemical reaction. How much reactant is transformed to the product, and this is very important about to calculate the quantum yield. The quantum yield can be defined as mentioned in the previous class is the number of moles of reactant. So quantum yield phi can be represented as number of moles of reactant consumed, number of moles of reactant consumed, or product form, or number of moles of product form, number of moles of product form. So the product form, number of moles of reactant consumed or product form in a given time t, or product form. Let's put it in the in a given time t, divided by the number of moles of photon, divided by number of moles of photon, moles of photons in terms of Einstein absorbed during same time. So this is how the quantum yield call is represented as phi is can be defined number of moles of reactant consumed or product form in a given time t divided by the number of moles of photon in terms of Einstein absorbed during the same time. So and then these parameter, how much product has been consumed, can be determined by any analytical technique like GC, HPLC, and so on and so forth. Whereas number of photons absorbed can be determined by actinometry, and there are several standard actinometries are available, that is uranyl oxalate, and so on and so forth. So we can, from this standard actinometry experiment, we can find out how much photon is absorbed by the molecule, and then we can calculate the phi. If the value of the phi comes out to be each photon absorbed produces one transformation, then phi is equal to 1 if each photon absorbed produces one photo transformation, then the quantum yield is 1. And then quantum yield is less than 1 when the deactivation process, like intersystem crossing, internal conversion, and so on and so forth, deactivation process is more prominent. deactivation process is more prominent. And then if quantum yield is more than one, then the chain reaction is taking place. A chain reaction is the chain reaction is taking place. So whenever we do a reaction, whether it is a catalytic reaction or photochemical reaction, we always talk about the yield of the product, and in terms of photochemical reaction, we call it a quantum yield. Quantum yield can be defined as the number of reactant consumed or product formed in a given time t divided by number of moles of photon in terms of Einstein during the same time. And then, as I have mentioned, the number of moles of reactant consumed can be determined by any analytical techniques like GC or HPLC, or whereas number of moles of photon in terms of Einstein in the same time, how much photons is absorbed, can be determined by actinometry experiment, and there are several standard actinometry experiments are available through which we can determine how much photon is absorbed. The it is possible to carry out these experiment in the same reaction vessel. uh, Same reaction vessel. If somehow sometimes the reaction vessel is broken, and then you and then you have to we have to determine this quantum yield experiment, actinometry experiment once again, because the light absorbed by the glass, thickness, length, and path length, and all are important parameters in determining the number of photon in terms of Einstein. So reaction vessel, the quantum yield can be carried out in the same vessel in which the photochemical reaction of any compound is determined. And as I mentioned, if quantum yield is found to be 1 if each photon absorbed produces 1 phototransformation, whereas quantum yield is less than 1 when deactivation processes like internal conversion, intersystem process is more prominent, and quantum yield is more than 1 when a chain reaction is taking place in this. So this is the fate of the. This is how we determine the quantum yield or efficiency of any photochemical reaction. So now coming to the next one is the Frank quantum principle. So this is an important principle. So, for example, and then this can be represented. First of all, we can define this electronic excitation. So, Frank quantum says that electronic excitation so fast are so fast so fast in comparison to nuclear motion, in comparison to nuclear motion, nuclear nuclear motion, that immediately after the transition, the nuclear matter so fast comparison with that immediately after the transition of the after transition, and the nuclei has the same relative position. The nuclei have the same relative position. So this is a definition of a Frank quantum principle, and it can be best explained by a simple representation of the diagram, where we can say that the so for example we have an energy here, and this is the we have a with the ground state curve, and then this is the ground state for a diatomic molecule by a diatomic molecule AB, diatomic molecule, and then say for example the molecule AB, and then there is the AB star. This is the ground state. We have a electron field, and then this is HOMO, and this is LUMO. And then in terms of energy, we can also represent like ground state is excited state curve. Now, in the in the excited state, we can have an electron. The in the excited state and goes to. So this is how excitation. So in a diatomic molecule, these are the nuclear motion, nu one, nu zero, nu one, nu two, nu three, and this is the nu one star, nu zero star. I mean V1 star, V2 star, and so on and so forth. So at one stage, when the nuclear motion can so longer that it may break. So this is the energy. So when this is the 0 to 0 excitation, the electronic excitation. What Frank Carter principle says that the electronic excitation is so fast that in the presence of as soon as the just electron goes up and then comes back, by the time nuclear motion changes its position. So electronic excitation is so fast compared to nuclear motion that immediately after excitation, not after excitation, after excitation, the nuclei have the same relative position. Nuclei have the same relative position. So the position of nuclei remains the same even so the it is and we can we can also say how fast is now is 10 to the power minus 15 second. It is so fast, it's 10 to the power 15 second. So you can say that it's very fast, electronic excitation very fast as compared to nuclear motion. So the nuclei changes relative position remain, they have the same position before excitation has taken place. So we continue this on the next turn with a few more revision what we have seen so far in the previous class. Thank you very much.